Well, of course, we all know what electrolytes are. They're something that we drink because we sweat. But actually, in chemistry, there's a broader, more broad definition, and there's a reason why we're concerned with electrolytes. And we can categorize them. Let's just say an electrolyte is something that will help conduct electricity when you dissolve it in water. And some would say even if you were to melt that thing, be it probably a salt. But on the other hand, some salts aren't soluble, and you could probably melt the salt into a liquid form, and it might conduct even if it was not water soluble. So I'm hesitant to say that. So anyways, so what are the electrolytes? Well, there's some strong electrolytes, there are some weak electrolytes, there are some non-electrolytes. The strong acids, you should know your strong acids break apart totally in water. So it might be a gas that breaks up in water. It might be more complicated than just a single step. But if you know what your strong acids are, hydrochloric, hydrobromic, hydriodic, nitric, sulfuric, chloric, and perchloric, then you know, and you should know those strong acids, I'm telling you. Because you know all the other acids are weak. There are hundreds of other weak acids. But if you know the strong acids, then you know that everything else is weak. And also, you know, the acids have the H in front. So when they dissociate or break up into ions, the H plus comes apart from whatever else is left over. Not bad to know the names also, if you can commit those to memory. So strong acids break up totally in water and become strong electrolytes. Same for the strong bases. We'll look at solubility rules in just a second, and we'll say that most hydroxides don't dissolve in water. Most OH groups, most salts with an OH group don't dissolve in water too well. But lo and behold, lithium, sodium, potassium, rubidium, cesium, strontium, and barium hydroxide do dissolve in water really well. And not only do they dissolve in water, well, that means they create ions in the water. And so I see the pattern of the naming. I see the pattern in the hydroxide. I see the pattern in the 1 plus versus the 2 plus. You should know your strong bases. And the soluble salts. There are many different ways to say what's soluble and what's not soluble. You could Google search solubility rules and look at the images, and you'll see all kinds of tables describing what dissolves and what doesn't dissolve. Nitrates almost always dissolve. Perchlorates, chlorides, iodides, bromides almost always dissolve. That's kind of a weird table. This one's also kind of weird, but worth looking at. But this one may be the best one of the best that I've seen. All nitrates dissolve in the water. All acetates dissolve in the water. Most chlorides, bromides, iodides, sulfates dissolve in the water. There's a few exceptions. Most sulfides don't dissolve in the water. Most carbonates don't. Most phosphates don't. Most hydroxides don't. A few notable exceptions. So the deal is this: if you know what will dissolve in the water, you know you can have an electrolyte. If you know what won't dissolve in the water, you know you might see a reaction if I were to mix two ions together in two different solutions. So what dissolves in the water? All nitrates dissolve. All acetates dissolve. Most chlorides dissolve. Most bromides dissolve. Most iodides dissolve. You can't memorize this, but you can see patterns, right? Most sulfates dissolve. Few exceptions to those: the insoluble non-electrolyte salts. Silver chloride doesn't. Silver, mercury, and lead chloride. Silver, mercury, and lead bromide. Silver, mercury, and lead iodide. Barium and strontium sulfate don't dissolve in the water, but most sulfates do. So these are non-electrolytes. They don't create many ions, if at all. All right, what are some insoluble salts? Most sulfides don't dissolve in the water, but sodium sulfide is an exception. So is potassium sulfide, lithium sulfide, cesium sulfide, ammonium sulfide. Most carbonates don't dissolve in the water. Frowny face. But potassium carbonate does, sodium carbonate, lithium carbonate, ammonium carbonate, excuse me, and all ammonium salts dissolve in the water, or almost all of them. So most phosphates don't dissolve in the water. Zinc phosphate doesn't, but ammonium phosphate does. Most hydroxides don't dissolve in the water, but lithium, sodium, potassium, rubidium, cesium, barium, strontium hydroxide do. Some would say that calcium hydroxide also dissolves, but not a whole lot. The non-electrolytes are even simpler. Well, I should say luckily simpler. They might dissolve in water. If they dissolve in water, though, they don't break up into ions. So we're talking the molecules, and we're talking hydrocarbons, maybe some oxygen thrown in there. Here's sugar. Dissolves really well in the water. Same for alcohol, dissolves really well in the water, but no ions are created. The molecule itself does not break up. And the insoluble salts. don't break up. So those are the non-electrolytes. Non means not, so the ones that don't conduct electricity when you put them in water. We can look at a bunch more of those, but often molecules, unless they have lots of OH groups, like the sugar does, you can't see it there, but it does. Unless it has lots of OH groups, molecules, solid or liquid molecules, may not dissolve in water very well. And the weak electrolytes. Weak electrolytes conduct a little bit, and those are like the weak acids. H, blah, blah. H, blah, blah. H, blah, blah. Whatever that blah, blah. Now, here's the deal. If the double arrows are seen, if you see double arrows, that means it's an equilibrium. That means there's some degree of forward, some degree of backwards. In the case of weak acids, it's mostly backwards. So out of 100 vinegar molecules, maybe 3 of them come apart to do this, and the other 97 stay together. Depends on what's called the equilibrium constant. But the equilibrium clues me off that it's not a strong acid. It's not going to come apart totally. It's going to kind of waver back and forth, sit on the fence. Same for weak bases. B is for base. Almost all weak bases are in the water, interact with the water, hydrolyze the water, and almost all weak bases have a nitrogen in them. And the nitrogen with its lone pair serves as a weak base in pulling the water apart a little bit. Out of 100 ammonium molecules in the water, how many of them do this? Now, like I said, maybe 2, 3. Depends on a couple of other conditions as well, but weak bases, weak acids, and slightly soluble salts. Again, double arrows. These equilibrium arrows mean lead chloride really doesn't dissolve in the water very well. So I lied to you a second ago. I said it didn't dissolve. It's insoluble. But does that mean that absolutely positively no lead ions and no chloride ions? No, a little bit. Most hydroxides don't dissolve in the water, but maybe iron hydroxide a little teeny bit. When I say teeny, I mean teeny. So small amounts, weak electrolytes. All right. So if you know what salts will dissolve and what salts will not dissolve, you might be able to predict a precipitation. Hopefully you've seen a precipitation in class, in the lab. I should show you one again soon, eh? So if I say mix silver nitrate with sodium chloride, what do you see? You see a precipitation of silver chloride because it doesn't dissolve. So the silver ion from this water runs into the chloride ion from this water, and they are so attracted to each other they grab on and form little wet crystals that no longer dissolve in the water. There's several types of equations we can write. We can write the molecular, or our text calls it the formula equation. I used to call it the total ionic equation. Our text calls it the complete ionic equation, where I break up all the ions and write them as ions separately. But over here I didn't break these up because that's not broken up in the water. It's come together as a precipitation. And then I cancel the spectators. The sodium plus, the nitrate minus cancel exactly on left and right. And my net ionic is much simpler than the formula or molecular, total, or complete equations. So this is just listing the species that do something. The net ionic equation cancels the spectators. What if I mixed lead acetate water? Most leads don't dissolve in the water, but lead acetate would. With potassium iodide water. Well, I'd get a precipitation of lead iodide because it doesn't dissolve. So when these ions hit 2 of these ions, they'll glom onto each other and sink to the bottom as cool yellow crystals of wet lead iodide. The complete ionic would look like this. Break up all the ions and mention them. Lead acetate in one beaker, potassium iodide in another beaker, throw them all in the mixture. You notice the potassium and the acetate don't do anything, they just float around. They're called spectators, but the lead iodide is insoluble. And that's what forces or pushes the reaction forward, is that formation of an insoluble salt. That ionic is much simpler. Let's do another one, barium sulfate. This is, barium hydroxide and sulfuric acid. This is a cool one because look over here. This is a liquid, there's no ions. This is a solid precipitate, there's no ions. But over here I got a whole bunch of ions. I got the barium and the hydroxide. I have the H2SO4. There's a little bit of a fib here. I'm simplifying, but I'm imagining if sulfuric acid is a strong acid, I'm just going to pretend that both those hydrogens come off of the sulfate. And that's not bad for right now. I'll leave it like that. But since nothing's over here exactly in common with anything over here, in terms of ions floating around, then I'm going to have to say there's no spectators, and the net ionic equation is the same as the total ionic equation. Interesting. The examples just continue and continue and continue. let's say, sodium sulfide mixed with lead chloride water. Well, most sulfides don't dissolve in the water, so when the sulfide ion hits the iron ion, guess what? They precipitate. Nothing actually happens to the sodium and chlorine. They're spectators. So I got 6 sodiums here, 6 chlorines here, 6 chlorines here, 6 sodiums here, left and right of the arrow. So yeah, they cancel. And the active species are iron 3 plus and sulfide 2 minus. Interesting, yeah? Ammonium carbonate plus zinc acetate. Well, you know what? Most carbonates don't dissolve in the water. So when this carbonate water hits this zinc water, they'll glob onto each other, they'll attract to make an insoluble salt, zinc carbonate. And I squeezed everything, all the ions in there. Notice the ammonium, 2 ammoniums, and 2, typo. Righto, I gotta stick a little 2 right there before I put this online. So there's a little mistake right there. 2 acetates, those should cancel. Zinc carbonate. So when you see this possibility, you can ask yourself the question, would the positive of the first like to meet the negative of the second? Or would the negative of the first like to meet the positive of the second? And when I say meet, I mean, will they form something that's insoluble to drive the reaction forward? Well, we all know sodium chloride dissolves in the water, so that's not going to force anything. It's going to stay dissolved in the water. But if you're just learning your solubility rules, you look up phosphate and see most phosphates don't dissolve in the water. So when this nickel water hits this phosphate water, they form the insoluble nickel phosphate, and it sinks to the bottom. I started off not having it balanced, and I thought I better balance it. So here's the unbalanced, and I went ahead and balanced it. And the total ionic breaks up all the ions, but then I see the sodium and the chlorine spectate, both sides, and my net ionic equation would look like that. That's just crazy. Thanks, guys. That's all I have for now. And like I said, the only thing to memorize on this are the strong acids and the strong bases, and some of the solubility rules the best you can. And we'll go from there. See you in class. Thanks for watching. Seriously.